KURINJI Senior Secondary School, CBSE, Namakkal.
Successful result producing school in state every year.
Administered by the Board of Directors with over 35 years of experience in the teaching field.
Special attention on art, craft, music, dance, silambam, yoga, skating and karate.
Focus on Hindi Sabha and Spell Bee Olympiad exams.
Smart class for effective and innovative learning and well-furnished library.
Solitary importance on sports and games in state and national level.
WhatsApp facilities to know activities of students and school inside the campus.
NEET, JEE, IIT coaching experts from Rajasthan and Andhra Pradesh along with our effective teachers.
Admission registration for classes LKG to +2.
KURINJI Educational Institution, Kavetipatti, Namakkal. Admission in progress. CBSE, KG to 12, contact 9025895176. Metric 6 to 12, contact 9344567484. For online admission, log on to www.kurinjischoolnkl.in.
In continuation to the last class, in this class we will discuss next continuation example problem, that is example 9.5. After that, we are going to discuss applications of elastic behavior of materials. Applications of elastic behavior of materials. Okay, right. First, see here. See the example 9.5. The average depth of Indian Ocean is about 3000 meters. Calculate the fractional compression. Calculate the fractional compression delta V by V of water at the bottom of the ocean, given that the bulk modulus of water is 2.2 into 10 power 9 Newton per meter square. Take small g is equal to 10 meter per second square. Now, the average depth of Indian Ocean is about 3000 meter, full stop. Calculate the fractional compression delta V by V, comma, of water at the bottom of the ocean, given that the bulk modulus of the water is 2.2 into 10 to the power of 9 Newton per meter square. Right. Anyhow, in this problem, we have to calculate fractional compression of water, which is delta V by V. Okay, right. Ipo, what are the values they have given? You know, H value, that is 3000 meters given, and density of water is a constant value, we know 1000 kg per meter cube, and then acceleration due to gravity value also given, which is 10 meter per second square. Ipo, the pressure exerted by a 3000 meters column of water, the pressure exerted by a 3000 meters column of water on the bottom layer, is, that is P is equal to H rho g, no, 3000 meters into 1000 kg per meter cubed into 10 meter per second square, that is equal to 3 into 10 power 7 kg per meter second square, kg per meter, so m power minus 1, s power minus 2, right? It is what? Kg m power minus 1, which is s power minus 2, okay? So, when it is kg m power minus 1, s power minus 2, that you can write it as Newton per meter square, Newton per meter square, so that we are getting there itself 3 into 10 power 7, right? See here, kg per meter per second square, right? Anyhow, there we are getting 3 into 10 power 7 in terms of Newton per meter square, in terms of Newton per meter square. Pressure value we got it as 3 into 10 power 7 Newton per meter square. Ipo fractional compression delta V by V is, that is delta V by V is equal to stress by B, stress by B, that is equal to 3 into 10 power 7 divided by 2.2 into 10 power 9, 3 into 10 power 7 divided by 2.2 into 10 power 9, that is equal to 1.36 into 10 to the power of minus 2, 1.36 into 10 to the power of minus 2 or 1.36%. 1.36%. So if we convert this into percentage, that is 1.36%. This is 1.36 into 10 to the power of minus 2, because it is fraction more, so which has no unit, or 1.36%. Delta V by V is equal to 1.36%. Right, that's what he is asking, we calculated. Now, next continuation theoretical topic, applications of elastic behavior of materials. Applications of elastic behavior of materials, right. See, in our daily life, if you see the cranes, and if you see the pillars, and if you see the mountains, and you can also see the wire bridge, and you can also see ropeway. So what I am talking is, the rope which are using to lift a heavy load is made up of made up of like iron like material. It is like a metal, right? It is like a metal. So there itself, what are the precautions we have to take? What are the precautions we have to take from the point of elasticity? From the point of elasticity, very well. For example, when a heavy load is going to carry by that is what in Ganesh Vinayak Chaturthi, right? There itself, the crane is carrying a heavy load Vinayaka statues. There are ropes, right? That ropes, how we have to make? See, what is the elastic limit, and what is the area of cross section, and what is the weight of what is the weight that the crane is going to lift by using these ropes? So it is nearly 10 tons. Okay, that's what we have to keep in mind, right? Regarding all those applications, now we are going to discuss one by one. Okay, that is what elastic behavior of materials plays an important role in our everyday life. Am I right? All engineering designs require precise knowledge of the elastic behavior of materials. Am I right? For example, if you are going to design a building, right, or the structural design of the columns, beams and supports require knowledge of strength of the materials used. Otherwise, what will happen? The building will collapse, the bridge will collapse, the engineering the engineering construction will collapse. So definitely we have to keep in mind what is the elastic limit, and what is the limit to carry, what is the limit to carry or to bear. Okay, right. Have you ever thought why the beams used in construction of bridges as supports, right? See, have a cross section of the type I, you can see, right? See, what is the shape of the pillar? That I'll tell you, in the same class, after 5 minutes I will show you the pictures, what is the shape of the pillar, right? And why does a heap of sand or hill have a pyramidal shape, right? So these are all applications. So the elastic behavior of materials plays an important role in our everyday life, right? At the same time, all engineering designs require precise knowledge of the elastic behavior of materials. For example, while designing a building, the structural design of the columns, beams, supports require knowledge of strength of materials what we are using there, either it is iron or steel, whatever it may be. Okay, and if you see the pillars what we are using, for example, if you go for Chennai metro pillars, you can see metro train, what is the weight, and it is a very huge, right? So what is the shape of the pillar, and what is the material they used, that is all very important. Okay, in modern day, as day by day the population has increased, right, we must need for the point of time, or for the point of comfortability, right, or for the point of safety and security. So we need a metro, right, we need bridges. Okay, that's what. So while constructing a bridge, not only bridge, so many things, but for example, we need to keep the elastic limit and the weight what that bridge has to bear. This is all in our mind. Okay, now we are going for one example series. One by one we will see. First we are going to see One best example, see here. Cranes used for lifting and moving heavy loads, that's what you know, from one place to another place, have a thick metal rope to which the load is attached. To which the load is attached. Okay, I will repeat once again. Cranes used for lifting and moving heavy loads from one place to another have a thick metal rope to which the load is attached. The rope is pulled up using pulleys and motors. The rope is pulled up using pulleys and motors. Is the best example is what that's Vinayaka Nimajjanam, right? Vinayaka Nimajjanam is there, no? So when Vinayaka, after completion of the festival, the statue we are going to put in the water. So there we are using meshes, the cranes with the heavy cranes. There you are seeing the same situation what I am explaining now. Suppose we want to make a crane which has a lifting capacity of 10 tons. That is our requirement, or metric tons, right? You just observe carefully how thick should the steel rope be, right? How thick should the steel rope be? Okay, that is how thick should the steel rope be, right? See here. To avoid deformation, extension. To avoid deformation, extension should not exceed the elastic limit regarding the mild steel. Mild steel has a yield strength of about 300 into 10 to the power of 6. 300 into 10 to the power of 6 Newton per meter square. Full stop. Thus, the area of cross section capital A. Thus, the area of cross section capital A of the rope should at least be A is greater than or equal to W by SY, that is equal to mg by SY, that is equal to 10 power 4 into 10 divided by 300 into 10 power 6, which will give us 3.3 into 10 to the power of minus 4. 3.3 into 10 to the power of minus 4 square meter. 3.3 into 10 to the power of minus 4 square meter. Okay, right, that is. Now, corresponding to radius, because the radius area of cross section also important, no? Because that only I told, while carrying or while lifting the load, the comfortability also important, right? As well as having bearable capacity of weight, but at the same time the comfort is also important to carry the same load what we are expecting. Here corresponding to a radius of about 1 centimeter for a rope of circular cross section, generally a large margin of safety is provided. Large margin of safety is provided. Thus, thicker rope of radius about 3 centimeters is recommended. Thus, a thicker rope of radius about 3 centimeters is recommended. Okay. A single wire of this radius, a single wire of this radius would practically be a rigid rod. That is the reason, if you observe those ropes are always made of number of thin wires braided together like pigtails for easy in manufacture, flexibility and strength. Okay, so it is a very good application regarding the ropes what we are using in cranes while lifting heavy load. Okay, that is. Now, for example, now we are going for another application, that is what bridge. Okay, see here, a bridge has to be designed, right? You know, you can see that the bridge with wires and bridge with, that is cement, steel rods and etc. So whatever it may be, but our requirement is to bear a lot amount of weight. That's what we require, and the safety and security is our main concentration. Okay, right. See, a bridge has to be designed such that it can withstand the load of the flowing traffic, the force of winds and its own weight. Right? Am I correct? Similarly, in the design of buildings, use of beams and columns is very common. In both the cases, the overcoming of the problem of bending of beam under a load is of prime importance. Right? The beam should not bend too much or should not break. Let us consider the case of a beam loaded at the center and supported near its ends. Near its ends. You can see in the picture, that is what you can see here. See how the bridge should be. It is the load on the bridge. Then the bridge may be like this, but it should not break or it should not bend too much beyond the elastic limit. Then it is a problem. It is a problem. So much traffic is there, so many vehicles are there, right? The peoples will die. It is like accident. Okay, right. Now, see, for example, consider a case of beam loaded at the center and supported near its ends as shown in the figure. This is what the figure. A bar of length capital L, this is the bar. It is the bar. You just that is what he is comparing. A bar of length small l, breadth, this is the breadth, right? Breadth, that is B, and depth, this is the depth, that is what D. Okay, this is the D. When loaded at the center by a load W, sags by an amount is given by. So regarding these dimensions, that is what length, right, and breadth and depth, right, and this is what delta, which I will tell you what is the delta. And here, regarding all these things, what is the amount that it can be bent? What is the load? I mean, what is the sagging, amount of sagging? That is what small delta. So how much it can sag means, see here, sags by an amount is given by delta is equal to W L cubed by 4 small b small d whole cubed small d cubed into y. You know what is y? Young's modulus. Okay, right. See here, W is the load that you know, and these dimensions I already told you what is L, what is B, what is D. D is the depth, B is the breadth, right? L is the length. 4 is, that is what a constant. See how we derive this relation means, right? So what we already know from those things we derived, but from this relation you can see to reduce the bending for a given load. See, we want to reduce the bending. It should not bend too much. It should not break. So to avoid the bending of too much, then what should we do? We should use a material with large Young's modulus because delta is inversely proportional to y. We should use a material with large Young's modulus. So for a given material, increasing the depth rather than the breadth is more effective in reduce the bending, since delta is proportional to d to the power of minus 3. Delta is proportional to d to the power of minus 3. That is the reason it is better to prefer the material increasing the depth rather than the breadth. Okay, and delta is also proportional to b to the power of minus 1, right? B to the power of minus 1. So finally what can I say is, but on increasing the depth, unless the load is exactly at the right place, the D bar may bend as shown in the figure 9.9b. So 9.9b means this is. See, it can bend like this. Okay. This is called buckling. Okay, ma? Right. Now, to avoid this, a common compromise is the cross-sectional shape. See, this is the shape. Cross-sectional, to avoid this buckling, this is the shape it is better to provide. This section provides a large load bearing surface and enough depth to prevent bending. This shape reduces the weight of the beam without sacrificing the strength and hence reduces the cost. So instead of having like this, it is better to have like this. So mostly we are seeing like this pillars only, right? Just now I told you, while explaining this information, I told you I will show you some pictures. So these are the pictures. So it is the shape of the pillar, right? To bear, this is the shape of the pillar which reduces the weight of the beam without sacrificing the strength and hence reduces the cost also. Okay, right. Now, use of pillars or columns is also very common in buildings and bridges. A pillar with rounded ends as shown in figure, this is what? Okay, this is what? A pillar with rounded ends supports less load than with a distributed shape. This is the shape. At the ends. The precise design of a bridge or a building has to take into account the conditions under which it will function. It will function the cost and long period reliability of usual materials. Reliability of usual materials. So this is the pillars or columns, right? And A is the pillar with rounded ends, and this is what pillar with the distributed ends. It can bear more weight when compared to this. So generally we will prefer this type, which will give us a long period, right, and reliability of usual materials. Okay, right. Now see the next one. See, I am going for another application, that is what mountains. If you see the mountain, for example Everest mountain, for example some other mountain, if you see that, you know, the bottom will be like is a very important, no? See, it is a natural thing, but I am talking about how that much of height will be. See, for example, the height of 8 kilometers, you know, 8 kilometers height means not that much of easy, no? Similarly, 5 kilometers height mountains, how the mountains are stable from years onwards, that is a very interesting question. The answer here you can discuss, right? See, for example, the mountain of the earth is approximately 10 kilometers, for example, you just imagine, because Mount Everest is 8 kilometers, so you just take 10 kilometers. By considering the elastic properties of the rocks under the mountain, okay, a mountain base is not under uniform compression, and this provides some shearing stress to the rocks under which they can flow, right? The stress due to all the material on the top should be less than the critical shearing stress at which the rocks flow, right? Okay, so regarding the shear component and the elastic limit of a typical rock under the mountain, we have to equate the elastic limit of a typical rock, which is 30 into 10 to the power of 7 meter per second square, to the h rho g, that is what pressure, right? Density of rock, you know, 3 into 10 to the power of 3 kg per meter cube. By equating the shear component and to this h rho g, right? That is what h means 30 into h rho g. H is 30 into 10 power 7, no? Right? So sorry, h rho g is equal to 30 into 10 power 7 Newton per meter square will come. See, that is what height we are taking, that we are going to find, and density I already told you 3 into 10 power 3 kg per meter cube, and g value, you know, that is 10 meter per second square. So by equating the h rho g to elastic limit for a typical rock, that is 30 into 10 power 7 meter per second square, we are getting the height as a 10 kilometers. So which is more than the height of Mount Everest. Okay, right. So in this class we discussed one example problem. There we calculated the fractional compression regarding the water, and afterwards we went to discuss, we came to discuss applications of elastic behavior of materials, right? There we had different applications. Now the first application is the rope what we are using regarding the cranes to lift heavy load, nearly 10 tons. Next application we came to discuss the shape and the size and shape of the pillars regarding the bridges, right? So this is the shape generally we are using, and this is the shape also we are using regarding, we don't want to lose anything, we don't want to lose cost, we don't want to lose the reliability, we don't want to lose the that is what time period of working, we don't want to lose the safety and security. By considering all these things, so which is better that we are going to consider, right? That is our ultimate requirement, right? Next, last we also discussed the application of mountains. So what about the rock which is under the mountain? What is the height? That is 10 kilometers. Regarding the elastic limit for a typical rock of 30 into 10 to the power of 7 Newton per meter square. Okay, right. So this is the last class regarding the chapter mechanical properties of solids. So in our next class we will start next continuation chapter, that is mechanical properties of fluids. Okay, right. Thank you.